Alrighty, how's it going today? Alright, well, so announcements, which I guess most of the class isn't here for, but you're here. So I want to remind you, I posted an announcement. Scott is teaching a machine learning class in spring. It's 2 credits. It's going to be Mondays from 3 to 5. If you have space in your schedule, check it out. It should be a good class if you want to sort of get an overview of what machine learning is all about and what it is and isn't, right? This can be a good introduction to it. So that's a CSE 280 course. So that's in spring. Second announcement reminder, make sure you upload your SLP poster by Monday at noon. Okay, they go to the printer Monday afternoon. Please, please, please upload it. Okay. Download the template from Canvas, fill it in. And it's a guideline. You can modify it however it makes sense for your project based on where you are. But, you know, basic look and feel comes from the template. So that's due Monday at noon. Third announcement. So I went ahead and posted a study guide for the final exam. Just as a kind of reminder of what we've talked about and hopefully where we're going before the course ends. Not everything we talk about turns into a programming assignment in this course. Okay, for example, we're going to talk about tree balancing today. You're not going to have a programming assignment on tree balancing, but you're responsible for understanding tree balancing. Okay, we talked about queues yesterday. You're not going to have a programming assignment in queues, but I want you to understand queues. So the final exam will be a combination of some programming questions and some non-programming questions where, for example, I might give you a queue and some code to manipulate it and ask you to show me how the queue gets changed when you insert and remove. Or I might give you a tree and ask you to use the rebalancing algorithms we're going over today to balance the tree. Okay. So I've put those topics on Canvas under the final exam study guide. Some of them we haven't gone through yet. But if you're coming to class, this is good, okay? Because yesterday, you know, we talked about queues. Queues will probably be on the final exam. And so if you're checking into class once a week and picking up the large pieces like the programming assignments, right, you're going to miss a lot of details. So that's part of why I put it out there. This also means that as we're talking about things, if questions come up, please ask, okay? Or if you go home and you think about it and you don't understand something, come back the next day, ask. Right, what was the deal with the rollover in the queue or whatever? All right. So any questions after that?
Just thinking about a queue. I was implementing it last night for PA4.
Mm-hmm.
I was thinking linked list versus an array.
Mm-hmm.
And trying to understand what the pros and cons would be. Obviously, you'd need a dynamic array if you know the size. But
Right.
I was reading that the linked list has a better worst case runtime, but typically an array will be a better average time per operation. Not like asymptotic analysis, but just per operation.
Oh, per operation.
The array would be more efficient. But
You have to do more work for a linked list because you have to allocate memory and you have to free memory. But that's pretty marginal, unless you're spending a lot of your time doing a lot of inserts and removes. That's a pretty marginal factor probably. It's usually just, you know, an array is pretty quick and dirty, but if you have a linked list package, that's pretty easy to use.
So if you run like a billion or something like that,
Mm-hmm.
would an array be much faster because it's not using dynamic memory allocation during runtime?
Probably, yeah. Yeah, I mean, if you're inserting and removing a billion times, that's a lot of memory manipulation. So
That's pretty expensive relative to an array.
compared to just writing into memory or reading from memory, yeah, definitely. I mean, just making a function call is expensive, plus all the heap manipulation inside the operating system. But, you know, again, try it. Do a million mallocs and trees and see how long it takes. I really don't know what the numbers look like.
It's in a huge database or something like that.
I can just insert and remove something a billion times.
Yeah, I can do that.
Yeah. And I don't know how much mallocating memory defeats cache. Like, I don't know if you're getting the same memory locations back again and again, and if your cache memory is able to take care of it or not.
Okay.
But yeah, it might be
I'm not
interesting
exactly what you
analysis.
mean by that. I'm not super familiar with cache memory. What do you mean by that?
Cache memory is basically the idea that usually you access memory from similar locations.
Okay.
And so if you access this one location in memory a million times, it's much faster than a million times what it takes to access it once. The first access is expensive. It has to go usually out to main memory, possibly out to the hard drive. But once you've pulled this into your CPU, a copy of it is kept locally. And then if you ask for it again shortly after, it just takes the local copy.
Is there a way to control that from C programming to make sure that you're optimizing that? Or is
Not
that
directly.
lower level than that?
That's much lower level.
Okay.
That's down to the hardware level usually,
Okay.
sometimes inside the CPU chip itself. But there's ways to certainly circumvent it. There may be ways to precede it. That's all good operating system and computer architecture stuff. All right, so let's balance some trees. So remember the basic drill. There's a tree containing 7 pieces of information. There's another tree containing 7 pieces of information. They can both be binary search trees. We can process them recursively and so on and so forth. If we're searching for something, say we're searching for this last piece of data, in this tree we're going to have to do at most 1, 2, 3 operations. In this tree we would have to do 7 operations. Okay, this is basically a list. If you have a big long line of nodes, n nodes, you've got to move n hops to get from the root to the last node. In a nice fluffy tree, you have to move roughly log n hops, right? It's the height of the tree. So balanced trees, trees that tend to be very short and wide, are more efficient for searching and inserting and deleting and doing everything that you want to do with trees, other than recursing. And depending on how your data arrives, right, if you insert numbers like 20, 10, 30, you're going to end up with that kind of tree. If your data arrives like 30, 20, 10, you're going to end up with this kind of tree. So depending on how the order comes in, your tree may be balanced or unbalanced. Typically, it's going to be pretty unbalanced. So it's hard to take a tree that's unbalanced and turn it into a balanced one. Okay, that's a lot of work. What's not so hard to do is to take a balanced tree, add or remove one node, and then make sure the tree remains balanced. If you're starting with a tree that's already balanced and you want to add one more node to it, it's not too bad to restore balance. So suppose we were getting our data in this order. So there's a 30 and there's a 20. There's our tree. That's balanced. Okay. The left side has a height of 1, right side has a height of height of 0 and -1. That's within 1 of each other. And that's balanced, and the null is balanced. So this is a balanced tree. We get our third piece of data, 10. We put that on the left. If at this point, before we bring anything else in, we look at this and we analyze it and we discover that it's unbalanced, it's really easy to fix. In this case, we can do what's called a rotation about the 20, which basically takes this node and brings it down to the right. And it would turn this tree into this. And that's nicely balanced. And then if you've got 20, 10, 30, and you insert a 40, that is still a balanced tree. And then if you insert a 50, that's unbalanced, but we can do a rotation about the 40 and basically turn this into 40, 50, 30, and then leave the 20 as the root, the 10 to the left, and that's a balanced tree again. So the process of keeping your trees balanced is the following. One, make sure you're starting with a balanced tree. And if you're starting with an empty tree, that's balanced. Two, anytime that you add or remove something from the tree, check to see if it's balanced. And if it's unbalanced, make a correction. So these are called AVL trees, three people's initials. Who came up with this algorithm? So the first question is, how do we know if the tree is balanced or not? And so we define a balance factor. And balance factor applies to each node of the tree. And we're going to define it as the height of the left subtree minus the height of the right subtree. So there's a kind of unbalanced looking tree. So let's start from the root to define these. So this node, left side subtree and the right subtree are null. They both have height -1, their difference is 0. So the balance factor is 0. So I'll put my balance factors in purple, which looks the same as green up there. Alright, same thing over here, balance factor will be 0. This node right here, left and right subtrees both have height 0, balance factor is 0. This node, the left subtree, has a height of what? This is a pop quiz. What's the height of this 3-node tree? That's 1, good. Right, because it's 1 hop from the root to the deepest node. So this has a height of 1. The right subtree of this node is null. What's the height of a null tree? -1. So 1 minus -1 is 2. This has a balance factor of 2. This node over here, left and right children and all, that has a balance factor of 0. And then the root of the tree, the left subtree, has a height of 2, right? I'm not looking at the balance factors, I'm just looking at the height. Longest path from the root to a leaf node is 2 hops. So this has a height of 2. This has a height of 0. 2 minus 0 is 2, so the balance factor of the root is 2. All right, understand balance factor? It's just a calculation on each node. Difference between the left subtree's height and the right subtree's height. So in my heavily pathological tree, like this node will have a balance factor of 0 because left and right subtree are both the same height. This node right here, the left subtree is null, that's a height of -1. Right subtree is 1 node, that's a height of 0. -1 is 0. -1 minus 0 is -1. That's that node's balance factor. This node, left subtree, has a height of -1. Right subtree has a height of 1. -1 minus 1, this has a balance factor of -2. And the pattern will repeat. Okay, the larger the magnitude of the balance factor, the more unbalanced your tree is at that point. Right? This is a -4, it tells me at this point I've got a lot more stuff on the right than I do on the left. +4 would be the opposite, a lot more stuff on the left. So it turns out a tree is balanced if and only if balance factor of node absolute value is less than or equal to 1 for all nodes in the tree. So if you have a balanced tree, the balance factor everywhere will be 1, 0, or minus 1. And if you find a balance factor bigger than 1 or less than minus 1, your tree is not balanced. All right, so let's run our sample again. So let's build a tree by inserting a 10 and a 20 and a 30. So start off with an empty tree. When we insert a 10, we're just going to make a node containing a 10. When we insert a 20, we'll start at the 10, move to the right. There's nothing to the right, that's where the 20 will go. And at this point, this has a balance factor of 0, and this has a balance factor of minus 1. So the tree's balanced. Now we insert a 30. 30 is going to go to the right of 10, to the right of 20. It goes right here. This has a balance factor of 0, minus 1, and minus 2. And our tree is unbalanced. So we have to make an adjustment, something called a rotation. And there's 4 possible rotations we can make to restore a balance. So there's a cool little table I pulled from Wikipedia. And looking at the balance factors in your tree, you will find that you are in one of the following cases. Balanced, right? Or balanced to the right, balanced to the left, or balanced a little bit to the right and left, or left and right. Okay, we have a balance factor of 0, minus 1, and minus 2. So we're looking at the place where the imbalance occurs, the 2 or the minus 2, right? And we're in what's called the right case. Okay, we have a node that's got a factor of minus 2. Its right child has a factor of minus 1 or 0. Either of those means this is a right case. The intuition is the child of this node is too heavy on the right, and the child of that node is also too heavy on the right. So we can balance this by rotating and bringing some of this over to the left. And so there's a nice prescription here for how you do this. If we think of that node that's got a balance of minus 2 as node 3, its left child is A, its right child is 4, that node's left child is B, and so on. To balance it, we change 4 into the root. Node 5 and its children does not change. Since 4 is going to be the root, its left child is going to become 3 instead of B, and then B is going to get picked up by 3 on the right. So if we think about applying this right case to this tree, this is node 3. Node A is null. This is node 4. Node B is null. This is node 5. And C and D are null. And the balanced version would still have node 5 down here with its same null children. The root node would be the node that's node 4, which is our 20. 20's left child would be node 3, which is a 10. And then if 10 had a left child, that would stay on the left. And 10's right child would be whatever had been to the left of 20. So it takes a little practice to get fluent in using these, but we'll do a few of these up here, and then I'll let you do these on the board in groups. And I've got copies of these that you can use. But let's just run through some of these. So there's our restored balance to our tree. Bring in a 40. That's going to go on the right. That's still going to be balanced. Let's bring in a 5. And now if we calculate our balance factors, this will be a 0. This will be 1. This will be 0, this will be 0, this will be minus 1. And if you want me to work those out for you, say so. But I'm just doing height of the left subtree minus height of the right subtree. Yeah?
I'm getting a little confused on what's 0 and what's -1.
So this is saying the height of the left subtree is 1, the height of the right subtree is 1, 1 minus 1 is 0, that's the balance factor of this node. Okay, this node, the height of the left subtree is 0, the height of the right subtree is -1. 0 minus -1 is +1. This node, the 30, the height of the left subtree is -1, height of the right subtree is 0. -1 minus 0, this has a balance factor of -1. Okay, so balance factor, I'm always just doing height of the left minus height of the right. So this is still balanced. But now if we put in something like a 7, we recalculate our balance factors. So this has null children on the left and right, so this is a balance factor of 0. This node, -1 on the left, 0 on the right, this has a balance factor of -1. This node, left subtree has a height of 1, right subtree has a height of -1. This has a balance factor of 2. So this tree is unbalanced, and it's unbalanced around this 10 node. And if we look at our cases, if we have a node with a balance factor of 2 and its left child is -1, that's a left-right case. Okay, that's what we have here. So let's just apply these corrections to this tree, and let me copy this over onto a fresh page. So we have 20, 10, 5, 7, 30, 40, and the 30, 40 aren't going to come into play here. And this has a balance factor, let me put these in parentheses, 0, -1, 2. Alright, so we've got a 2 and a -1, and then other stuff after that. Okay, so the parent of this node, right, this is where having colors that actually look like colors would be really useful. So let me call this node 3, let me call this A, let me call this node 4, B and C are null, this is node 5, this is D. Okay, so 5 and D are going to stay the same, but node 4 is going to become 5's left child. So let's make this adjustment. So we're going to go left, right. Okay, node 5 remains the root. This is node 5, this is D. 5's left child is node 4, that's going to be the 7. 4's right child is going to be C, well, that was null, so there's nothing on the right of 7. 4's left child is going to be node 3, which is the 10. This isn't right. I did start with a binary search tree. Oh, I numbered these wrong. Okay. Let's just start that fresh. All right, balance factors in parentheses. So this is a factor of 0, this is -1, this is 2. All right, so the factor the node that has a factor of 2, that's node 5. Okay, D is hanging on its right, that's null. This is node 3, A is hanging on its left, that's null. This is node 4, and 4's children are B and C, those are null. Okay, so the left-right adjustment leaves 5 as the root, so that's still 10. its right child would still be D. That's just null. Its left child is going to become node 4, which is the 7. And node 4's left child is going to become node 3. That's the 5. And then everything else in the tree stays the same. So this is going to be a 20 and a 30 and a 40. Okay, this is still not balanced. What it's doing is it's changing this type of unbalance where we're going to the left and the right into a case where we're going to the left and the left. Okay, so if you have a left-right imbalance, this rotation changes you to a left-left case. Same thing if you're right-left, you can change into a right-right. Okay, so this is our node 5. This is our node 4. This is our node 3. So what's the rotation from left-left? Node 4 becomes the root, so 7 comes up here to the root. 3 stays on the left of 4, so that's our 5. And then node 5, which was a 10, moves to the right of node 4. And then the rest of the tree stays the same. So that's what our tree gets changed into. And if we calculate balance factors, that's balanced, 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 and this is -1 and 0. This is -1, and the root node left subtree has a height of 1, right subtree has a height of 1, so this is a balance factor of 0. Alright, so I'm going to have you do this on your own in a minute, but let's make sure that this is sane. Because, you know, it's easy to move nodes around and make things balanced. The trick is moving things around in a way that keeps this as a binary search tree. Right? We can't just take a node that's over here and pop it over on the right side. We need to make sure everything on the left of a node is smaller, everything on the right of a node is smaller. So let's look at the in-order traversal of this left-right case. So just suppose this is the whole tree, and we're doing left node right. Okay, we're going to go to the left, we're going to go to the left. First thing we're going to traverse is everything in this subtree called A. And then we'll visit the root node 3. And then we'll traverse this tree using left node right, which means we'll traverse everything in B. And then we'll visit the root node, and then traverse everything in the right subtree. That is the left node right traversal of this thing. Then we visit the root node, and then we do the left node right traversal of the right subtree. So that's the traversal we get from this original tree. When we change it into the left-left case, what's the traversal of this? Well, if we start off, we go to the left, we traverse this, we traverse this. We're going to traverse this subtree in left node right, which is going to be A, 3B. That's this tree's traversal. Then we traverse the root node 4. And then we traverse the right subtree C. That's this subtree's traversal. Then we traverse the root of the original tree. And then the root right child, which is D. So A3B4 C5D, A3B4 C5D. So the traversal order of this is the same as the traversal order of the original. We haven't disturbed its property of being a binary search tree. And then if we apply this rotation to make it balanced, this one's easier to traverse. It's going to be A, 3, B, 4, C, 5, D, and that's the same traversal order. So these rotations are faithful to the property of this being a binary search tree. It takes a little more work to show that after you make these rotations, things end up balanced the way that they claim they do. But that's not too hard to show. But we'll take it on faith. All right, so you want to try this? So go ahead and break into groups, and each group come up and grab one of these cheat sheets, find a spot on the board, and I'll start giving you some nodes to put into a tree. All right, so start off, just insert a 20 and then insert a 10. All right, and then go ahead and insert a 5. And then go ahead and write down the balance factor next to each node.
The balance factor here. That's 0. That's going to be minus. I do that right? Yeah, left. What would be the balance factor for this this height here is 1, 0. Here would be, oh wait, that's right, 0, 1. And then 0, negative.
So check your factor on the 10.
Yeah.
So balance factor is height of the left subtree minus height of the right subtree.
So the height of 0, this guy's negative 1.
Cool. All right, good.
Whenever it's a null, we can even draw it, but like,
Check the height of the 20 again. That's too good.
not the null out here.
All right, height of the 5.
Why is it?
There you go.
Yeah, minus.
And then height
Oh,
of
yeah,
the
they
10.
will.
Yeah, the 10 would be this height is 0,
So it doesn't-
minus 1.
Yeah.
Makes sense.
Yeah, that's how I got through it.
All right, cool. 20.
Minus 1 minus 1.
Cool, perfect. All right, good. Everybody looks good on that. So yeah, if you haven't already done this, go ahead and identify which case that is. Yeah. All right, and then apply the rotation.
Rotate. That's one grab it.
All right, cool. Everybody's got good data on that. Let's insert a new number. So let's go ahead and insert a 40.
Into the balance tree or into the?
That one doesn't exist, just the balanced one. Yeah. So yeah, insert a 40 into that new tree. And then go ahead and write down your balance factors.
This one has a height of negative 1 minus 0 minus 0. That's 0. This one height of 0 has a height of 0 minus 0. 0. Is that right? We do the left first. Yeah. Okay, so the height of 0 minus the height of this. Yeah, we already have a height. So it can be. Yeah.
And so check the height of the root node.
So is it gonna be one minus one?
Minus height of this.
That's
one. It's zero. Negative one minus zero. And the height of this is
That's how we
the
got
height of
this.
this minus the height of this. Sorry, the height of this minus the height of this. So it's
The height of this.
zero minus minus
Minus
zero
zero
minus it should be negative one.
Yeah, it's positive.
Just one and a half.
Yeah, it is. So what's the height of the left subtree of
That
10?
balance.
Just the height of it. Right. What is left subtree of 10? 20. Left
Are you gonna try to do an AVL tree for not submitted? Do this. Try it.
Yeah. So it's just the node containing a 5, right? So what's the
Don't
height
do
of the
AVL yet.
node?
I'm gonna try it tonight.
Okay, so that's a 0. What's the right subtree look like?
Definitely.
So the right subtree is just that, right?
Yes.
Okay, what's the height of that tree? That's 1. Okay, so 0 minus 1? Minus 1, there you go. Good, all right, cool.
Yeah.
So is that balanced?
Yeah.
That is balanced. All right, let's upset it. So let's add a 60. And recalculate your balance factors.
So it would have a balance of -2.
Zero. It's negative one. Zero. Zero. Do that right. Negative one minus this one.
So when is it -2?
Yeah, zero. Minus. Zero, minus 0, 1, 2. Yeah, that makes sense. So it should be the same as this one. Checking on that. Not sure. Negative 1 minus 0. Negative 1 minus 1. 0 minus 0 minus
Well, I was kind of saying that.
All right, and if you got the balance factors, go ahead and figure out what case you're in and then do the rotation. Okay,
Yeah, we don't use. Okay, right. So we definitely use the right case.
Yes.
So if we keep adding trees down, it would just, this is
We're in
-3,
right case.
That should be -2,
And we
yeah.
add another one, it'd be -3, another one -4.
Yeah. So you see why that's -1?
We'll just pivot up. And
So the 20, the left subtree is null, right? That's got a height of -1.
pivot up that.
The right subtree has a height of 1. Yeah. it does. So if you have a tree like this, maximum number of hops from the root to a leaf is 1. Okay. So the height's equal to 1. You have your null tree, the height's equal to -1. Right? Negative 20. Yeah, the balance factor is -1 minus 1. That's
It's gonna be the same on both sides. 0.
And they're weird because they almost make intuitive sense, but then they don't. I was confused with that balance factor. Yeah.
This one is 0 minus.
That pretty much is called.
Cool.
He pretty much gave these two.
Is that right?
Let's see, so which case is this?
This was, you got it at 60?
Right, so which kind of imbalance is it? It's a right case, okay. So, yeah, so node 4 should come up in place of node 3, and this should go down like that. So the effect is basically take that, and do that.
Because we start kind of 0, so 0, 1.
I think that's,
Oh, it's -1 node, so you got some here. That's going to -2 node to it's -1 node. So you find -2 node. Then you take a -1 node.
So the effect of these rotations is when you're in a right case and you're trying to balance, basically you're taking this link here and you're just turning it down like that. Right? Take the 20, 40, bring it down so the 20 is to the left of the 40, and then move this up where the 20 was. Okay? That's why it's called a rotation. And so you end up with this. Perfect. All right, so let's continue. So we've got a tree that looks like this. Let's go ahead and add in a 30. Yeah.
Okay, now we got left, right.
Say again?
Right. To be a left, right, yeah. So we do the height.
It might look like that's the best, but it's not the algorithm. But yeah, there are different ways you can balance it. That might make it more balanced. But it's hard to tell a computer to notice that.
-0.
But yeah, you're absolutely right.
1.
Did you explain how it works with the
One.
or 7 minutes?
Yeah.
I was like 14 minutes or so.
Okay.
0 minus.
Do you mind if I ask about 10 minutes? Why not 14? Well, just math.
Yeah, so if you came in late, there were a bunch of really important announcements in the beginning of class also, so make sure you go back and watch the video or get notes from someone about things like the final exam and stuff.
First we gotta convert to right case. Left. So if we switch up over here. And if we just here, then we. So in order to do the left right case, you can't immediately announce it. You have to convert to left right case. Right, so it's a two-step process. Up here we just got this step, so we can just go to the next one, which is the last one. So left right case. The left right case will change to 0, and then you
All right, once you have balance factors, figure out which case you're in. Let me eyeball.
Right left case, is that right case? Is the same?
This is like the pool, right, this node. We want to
Oh,
move
that's
it
what,
up here.
yeah.
Fake. 20 of it fake.
From there, we rotate towards
It's left minus right.
I have no idea how this is kind of silly.
I know what I want to do. I just would do it with the algorithm. Because we want to pull the one we replaced it into this slot, which would make it left right. So if it was a left right case, we pull this up here, we put the 40 here.
Yeah, I don't know the tree.
It's like it's like math, but like
We did in fact calculate it.
yeah. There was
I didn't say very clearly that this shape. So 3.
One always like one minus 2, and the knife always does 2, and it gives you
Oh, the C. See how the two
you're
have
like,
the C.
oh, they
So you can pull all the way down here.
it's
So
like
in this case, the C would be our 30. This guy goes, this 40 goes immediately right.
yeah, for extra
And so we sort of like save the 30. We're going to put it all the way at the end.
but
And
in order
then
to
we're
get
going to
it gets to score the top 35% positive scores. I think that's not just for college, that's all of
put the
it.
5 in, and then we print
There's not no point unless you only compare process for the
All right, so everybody got the balance factors, and that is a right-left case. So do a rotation to bring it to a right-right. So let's see, so that was your original tree. All right, so what did your first rotation do?
What I did, this isn't my one.
So what's the balance factor at the 10?
That's what we do, right?
Because we would roll 0 minus 2.
Mm-hmm.
Yeah, so back to this tree, I guess.
All right, so that's where you got an imbalance.
Okay, this. We want to end up pushing this guy here. Taking
Yeah, that's a
his
right-left
C,
case. Now you want to rotate it to the right-right case.
So we like combine
left,
a left right case with a right left case?
So you're going to
It's like we did it right.
leave the 10 where it is. Left child is going to stay the same. You're going to basically swap
myself.
those two nodes below it.
Okay, so yeah, we did it correctly.
Okay,
Now we
40
do one
and
less step. Now we have a right average.
20.
And then,
Now we gotta go to balance. So we did went from here, now we got balance. There's balance. We're just gonna pivot off these guys.
So it's okay.
Well, let's do the look factor. So it's 0. This guy is also 0.
so,
This guy
So
is 0.
that's not quite right, but you lost
So
it.
it'd be -1 minus. And this guy, 0, 1, 2.
Yeah, right?
0.
So when you're gearing up to do one of these rotations, it's helpful at first to try to label these nodes based on this picture here, right? So this node up here is 3. Let me put these in boxes. That's node 3. This is subtree A. This is node 5. This is subtree D. This is node 4. This is subtree C. And then you can just piece them together the way that the rotation says to. So 3 is going to stay at the root. A is going to stay on its left. The right child of 3 is going to be node 4. That's our 20. The left child of 4 is going to be B. That's still null. The right child of B, of 4, which is our 20, is going to be node 5. That's our 40. The left child of node 5 will be C. That's our 30. And the right child of 5 will be D. That's 60. So this is a result of doing the right-left rotation. And then if you calculate the balance factors, you'll find you're in a right-right case and you do one more rotation. All right, so we'll work on this more tomorrow. I'll take the yellow sheets back unless you want to hold on to it. To practice on these. All right, I will see you next time.
Hey, so Nick,
So what?
I was wondering for the